I want to go through a few concepts about some of these estimators. We've been just talking about what these estimators are, their good ideas, but let me give you some guarantees and tell you some things that we can prove, and I'm going to give you some proof outlines, at least with a picture, give you the conceptual idea, try to make you think that the concept is sound, and then see if you can butter up the proof and like add the proof in there. If you'd like to go through formal details of how to actually set up formal proof, we can do that in review next time. So this coming Thursday, we'll have a review session. Sorry, let me re-say that. Next Thursday, we'll have a review session, so not tomorrow.
Better.
Is that better?
Yeah.
My phrasing is better, or just better for you?
It's better for us to do a test tomorrow.
Ah, yes, exactly. So I'm going to be considerate. So we'll hold off. Yeah, definitely. This is that time of year. I sympathize, but just keep your foot on the gas. One thing you can always predict is this is the hardest time. So. Okay. Let me make it a little bit harder and add some concepts in here. More things to remember. Hopefully these aren't too challenging of concepts to remember. I think of my proofs as pictures or just concepts first, and then I build a proof out of them. We know what risk functions are, and we know what the Bayes estimator is. So it's just this thing. I can write that as a double integral. So I'll just do that real quick. Argmin over E, integrate the risk function, which is just the expected loss. F of x, given theta, dx. So we're seeing what happens on average in terms of the data. So this is omega x right here that we're integrating over. And then I'm going to integrate with respect to some weights on theta. And so I'm not going to think about any like super useful properties or priors. I'm just going to explain this as if you want to upweight or downweight different parts of theta, then you have the ability to do that through pi theta. And so I'm kind of giving you a subjective view of it. Of course, Bayesians sometimes pick certain priors based off of different reasons depending on what the parameters mean in their distribution. If you want to know more about that, take a full-blown Bayes class. And I'll fill in those details of maybe how you select the priors. So that's what Bayesians are doing, is they're basically picking the estimator, so this thing, that minimizes the average risk. So if you haven't thought about this in terms of a function, I could end up just drawing this right here. So risk, bless you, is a curve. So I can just write risk in here. It's a function of theta, and I've got some curve for some estimator. So if I compute this, this is a function over theta, and I can just draw that. And so where this curve is a little bit lower is telling us that it has less risk. And what a Bayesian is measuring is the area under this curve. And they're optimizing that and trying to minimize that area and saying that it's low on average, which seems like it could be a good idea. Let me just butter up my notation. I'm going to be a little bit inconsistent about this. I just want to give this one more label, that this is a function of that estimator right there. So that estimator's in there, and we're going to do something with it. So I'm just going to write in a little bit more notation. You don't see it right here in the notation, so I'm a little bit inconsistent, but we know this is a function over E. So I can end up writing that right in there if you'd like. So this is a risk function for some estimator. I'll call it E1 theta. So there's other estimators that have other risk curves. So if I had another estimator and it did something like this, then I might say, well, it depends on where theta, what theta is. To whatever theta is, it's going to define what estimator is better. So if the true theta was over here, then this risk for E2, call that estimator E2, is a little bit better, but after they cross at this point right here, things switch. And that's what makes this a little bit complicated, is that different estimators can perform differently in different parts of the spaces. And so, and we kind of know that from our Bernoulli examples, that when P is in the middle, there's all these different trade-offs versus when P is over at the endpoints. And so it's interesting because P in the middle of the space where everything is 0.5, you have a lot of variability. You get to see a lot of ones and zeros, things like that. And it's that variability that gives us the ability to distinguish and figure out what P is. If there was too much variability, that would overwhelm us. So we kind of want that right sort of balance in there. But over the endpoints, there's not enough variability. For low sample sizes, we don't get to see enough ones or zeros, depending on which side of the endpoint we're on. So estimators don't perform always uniformly. I will tell you for a normal example, mu, if I were using the L2 loss, if I were trying to measure mu, X bar has uniform performance. So let's just figure this out real quick. So just an example. Xi is coming from a normal distribution with mean mu and variance sigma squared. I'll say that's known. Just to simplify things, if you didn't know it, you'd need to estimate it. X bar n is a typical estimator. And I can draw its risk curve. So the risk for, I'll just say R X bar mu, where this is the function of mu. Does anybody know what this shape looks like? Anybody tell me what that risk is? So I'm going to assume L2 loss. Oh, you're going to just stare at me and not do any thinking. This is the fun part when you have to think about it for a minute.
Is it just flat?
It's just flat. So what is that number? I did say this is flat everywhere. So it's flat. So that means it has uniform performance everywhere you go. What is this number right here? Just think about the definition. Thank you very much. Very awesome. So sigma squared over n, it's just the variance. Just think about the L2 loss function. That's a decomposition of bias and variance. It's a non-biased estimator, and all you're left with is the variance of that estimator. So boom. A fast way to do it. You could work really hard on that problem, but if you understood that decomposition, you immediately jump to it, the answer is pretty straightforward. So it's just the variance. And that's true no matter what mu I picked. It does not matter. So X bar is one of those things where it's, everybody agrees. You know, this is a good estimator. Question is this an optimal estimator? And in some sense it might be. So it might be a Bayes estimator. It might be a Minimax estimator. And in fact, it's both of those things. And so I'll tell you a little bit more about that in a second. So you get all kinds of desirable properties when we're talking about mu. That's why I sometimes like to jump to the binomial example, because you see differences in examples, in paradigms. I will say for the binomial distribution, X bar is not Minimax. So it's not a Minimax estimator. It's not the estimator that minimizes the maximal risk. So the name is really good. A statistician must have come up with this. So this thing right here is just the argmin over the maximum risk. And I'll say that's E right there. Use that notation. The argument's over the estimator, and I'm going to be maximizing over the theta space. So this is the Minimax estimator. I'll call it EMM, and just to bother you, I'll put that in the subscript. Just to get used to just rearranging things, different notations that people use. Would you have liked that one in the power? It wouldn't have mattered. Yeah, it's just that pi is always used already. Anyway, a lot of Bayesians do use pi is their notation for their posterior and their prior. Okay, so all very arbitrary stuff. So it turns out this is a Bayes estimator. a certain type of phase estimator. It's a phase estimator under the flat prior. So that would be the prior that you would use, and there's all kinds of good reasons to use that prior. And that's what stats is all about, all the reasons. So what are the guarantees? And they're not absolute guarantees, they're probabilistic guarantees. So this is kind of cool. So we already know we should probably use X bar. Here's one more reason: it has uniform performance. Do you think there's any estimator out there that could maybe beat this? Maybe has a risk function that's a little bit different?
Probably in certain values of mu there is.
Yeah, and certain values of mu. So let's say I wanted to optimize this on mu star, and I knew something about mu star, and you told me mu star. This question sounds really familiar, right? So let's say I wanted to make an estimator that absolutely predicted it had zero risk at mu star. How would I do it?
Mu star can be.
Yeah, just take the estimator is mu star. So under L2, the risk function would look like that. So this might be the risk function for mu star. That is my estimator. I'll just make it clear like that. Over mu. So it's just a parabola. So it's this parabolic function. I don't have any stochasticity to picking mu is equal to mu star. No matter what x is, I'll just give you mu star back. And so that would absolutely guarantee that the risk was zero at that point, but there's a lot of trade-offs. And the question is how far from mu star do you really think you could be? So if you thought that everything, no, I know that it's mu star. I'm just absolutely sure. So you wouldn't want to drift too far outside of that, and you wouldn't want to have a huge sample. Otherwise, it could be that even in some tiny little radius right here, this thing is smaller if n was bigger. So that wouldn't be a very good estimator to use. So would I use that estimator? I probably wouldn't prescribe it to people, but if people told me the answer is mu star and it never changes, so we just get this data that's a red herring, we don't really want to use it for anything, then maybe I would use mu star. But I've never been in a situation like that. So those aren't scientific questions. Okay, so that's one answer to one of your intern questions. So let me just rewrite this real quickly. I'll tell you more about phase estimators for a moment. I could rewrite this like this. Just our min is always out in front. And then I can rearrange all of this. So what I'm going to do for this is I'm going to pull the pi theta inside. I can do that, no tricks up my sleeve. So let me just rewrite that. Pi theta, if you will. So that's starting to look like a posterior distribution. If I gave myself just a little bit of room right here, wrote this dx, I can pre-multiply and divide by f of x. So f of x is just the margin. It's what happens when you integrate over that. So it means this thing right here is the posterior distribution. Pi theta given x. So that's the posterior. That's how we form it. So everything in the box is the posterior distribution. And then what I could do is maybe flip these things around. And if you want some justification on flipping those around, take a measure theory class, and they'll give you all these conditions, but in this case, you can flip this thing around. So I'm integrating over positive stuff right here. So this thing is positive, everything is positive. When everything is positive in the integrand, you can do that. So I'm not going to give you a proof of that, but we get pretty comfortable with this. It's the cases when you can't do this that's a little bit surprising. So check the regularity conditions, but everything falls in line here. We can flip things around. Bless you. So if you want to understand all that dominated convergence theorem and all that stuff, it's the permission slips for doing things like this. That's what you learn about in a more advanced inference class. So, but nothing too funny right here. And so then once I flip these things around, theta x, I can pull this thing right back out of that. So same sort of step like we did before, and I can write this integral down. Integral loss function ex measuring the differential between EX and theta. So in some sense, say you have to define what that distance is. So posterior distribution, d theta, fx, the margin, dx. But you guys would agree, for any problem that we have a fixed data set. So we've got some fixed data set, so we're building estimators conditional on that data set. So I can either think about this as averaging over all the different data sets to come up with an answer, but the answer is going to be exactly the same if I just use one data set and condition on it. Because when I'm minimizing over E, E only appears in this integral right here. So all I need to do for any fixed data set coming up with an estimator is optimize over this integral. So it's just a little bit of rearrangement. So E pi can also be found just by integrating over L EX, the loss function. Maybe myself just a little bit more room. So this thing is also equal to the arc minimizer over E integral LEX theta pi theta. And this is over everywhere. So all my integrals on the board are definitely intervals. They're over the whole space. Just as another example, and we've talked about this a couple times already. So an L2 example. L1 would be a little bit harder, but we would get a very similar answer. Again, if you want to see a problem in the book that has a solution in the solution manual, then we could discuss that solution next Thursday if you wanted to. If you're dealing with the median or the absolute, you cannot take derivatives over it. I have seen people do this since the first day I taught this stuff. Is they take the left-hand side and they tell me there's a linear line, and they take the right-hand side and they optimize over that, and they think that somehow breaking apart that absolute function into two different functions somehow solves it, and then you can take the derivative over it. So my calculus teacher said if there's a sharp point anywhere in there, you shouldn't be differentiating over the function. So, and that's actually where the optimum occurs. So no derivatives on an L1 example, but for L2, everything's pretty easy. I can end up just finding the optimal estimator just by integrating over the L2 norm. I'm just going to write my estimator as E. It's a function of X, but let's just call it E. There's no chain rule in here. If I want to butter up the notation, I can differentiate with respect to EX, but I'll just simplify it. Minus theta squared, that's the L2 norm, times the posterior distribution, d theta. So if I want to find the estimator, what I'm going to do is I'm going to evaluate this at E pi, and I'm going to set this thing equal to 0 to do everything. So what do we get when we do this? This is just integral 2 times E minus theta, no chain rule required. So if you want to add the chain rule, let's do 1 in there, d, bless you. So pi theta, given x, d theta. And then I'm going to set this thing equal to 0, and I'm going to call this e pi. So that would be like e hat, bless you, bless you, bless you. I'm going to assume those are allergies, so we have nothing to worry about. So, and then I just solve for everything. You can get rid of this 2 right here. This is not a function of theta, so when I integrate over one of these things, I can break this into 2 integrals. I'm going to have e pi times the posterior distribution. d theta is equal to the integral of theta times the posterior distribution, d theta. And again, these are all definite integrals. This is not a function of theta. You don't get to use theta in your estimators. If you use theta in an estimator, I'm going to think on the final, if you do this on the final, I'm going to think I didn't teach you very much. So please don't use the truth in forming an estimation. So the only time I would end up doing something like this is if you told me that's absolutely true. And the only time I think you would ever know that is in a simulation study. So it's not useful to apply in science or engineering. So this is the posterior mean. And this thing I can just pull out of that, integrate over the posterior. If I formed a posterior that's useful, it's a probability distribution and it doesn't explode to infinity. And it integrates to 1. So this would just be e pi over on this side. So e pi is the posterior mean. So for the L1 norm, and again, this would be very akin to 713 in the book, but of course you'd have to change the expressions a little bit. So it would be the posterior median if we were using the L1 norm. So I kind of like this setup because it tells me how to use this in an inferential sense. So conditional on some data set, here's the estimator that we get. Boom. So pretty easy. So we get all these same properties just in a different distributional sense. So it's the posterior mean is the thing that optimizes this. So it's always with respect to which distribution are we forming the mean. So a lot of Bayesians are just averagers, so we get paid a lot of money just to average numbers together, and our trick is to average with the right weights. So we come up with things in just the right way, but in a sense, I get paid a lot of money just to average. Okay, so that's a little bit more about Bayes estimators. I've told you what Minimax estimators are. Let me just say a few more things about this. Draw you a picture. Minimax estimators. So here's just an illustration of something that could be Minimax. So I'd like to draw this picture and think about it. Let's imagine I've got a whole bunch of estimators and all of their risk lives up here. So all other risk functions they live up in this space or above. So all other risk functions live up here, but I'm going to consider 2 other risk functions that live below. So I'm going to imagine one that looks like this. It's very good, except at some point, let's say its risk function is here. SoVe got some estimator. I'm going to call this RE tilde theta, with some estimator's risk function. It looks very nice, except at one point it kind of jumps up. And then I'm going to have some other function over here, and I could draw this completely flat, but I want to use this just to exemplify an idea. So imagine I have some other risk function right here. I'm going to remove that point, and I'm going to say its risk is right there. Now I could have made this flat and it would still be minimax, but I just want to just say everything happens for a reason, and it happens at one point, is why things are minimax. So this would be the minimax estimator's curve. So I'll say this is REMM theta. So just by the way I've taught it, I've looked at this, I've got all these other risk functions, they're maximums, or at least whatever this height is here. I've got a maximum right there risk on E tilde, and then I've got this other estimator, its maximal risk is this point, and it's the lowest one. And so that's the minimax estimator. So, and basically I'd like to just exemplify that, because what makes this minimax is not that point right there, it's this point right here on the other estimator space. So I have to think about all the other estimators and where they obtain their maximums. So it's not a question of where the minimax estimator obtains its maximum. So it's about this point right here. So I'll just call this theta star. to show you something that's going on right at that point. We're going to come back to this picture in a moment. When we try to prove a theorem, we're going to stare at this picture and come up with the theorem idea. Let me give you a couple definitions on domination and admissibility. So, in essence, let's start with domination. So really, I just want to build up the definition of admissibility, and I don't want to do it all at once, so I'm going to give you two definitions, just to layer our way up to a definition on when estimators are considered admissible. So, let me just ask you a question. Would you ever use an estimator that's inadmissible, just in terms, even if you don't know the language or exactly what it means? Is that a good thing?
Doesn't sound good.
Doesn't sound great. Yeah, exactly. Doesn't sound like a super thing. So definition. An estimator, let's give it a name. I'll call it E star. It has nothing to do with this star right here. I just run out of symbols. So an estimator E star is said to dominate another estimator I'll call it E tilde, so some other estimator out there in space, if two things have to happen. So the risk function for E star across all of theta has to be less than or equal than R E tilde theta. So basically the risk function has to be lower. So this is true for all theta. Now this wouldn't be very suitable because this could include equality everywhere in the whole space. So it wouldn't be very great if you were running a race with somebody and you tied them and they said, oh, you're not admissible, you don't get to come up and get a medal. But the person that tied you beat you. That doesn't sound right. So that could happen with this definition because everything could be equal across all of theta. So we need just one more thing to happen is we need RE star, let's just say at some point, theta star, again, not this picture, it's just some point, some notation, is strictly less than RE tilde theta for some E star. So it just needs to be strict somewhere. So the second condition is just breaking ties and saying you gotta be something. So that would be said to dominate because it's lower everywhere. Its risk function is lower everywhere. In this picture right here, these risk functions right here are dominating all of these, but neither one of these dominates each other. So the Minimax estimator is not dominating this other thing, but it certainly is dominating all of these.
There should be a star rather than a center.
Yes, thank you. So you get the idea. So perfect. So that's what domination means. So I'll say this. An estimator, so here's one more definition. That can be dominated by another estimator is said to be inadmissible. Makes sense, right? So why would I ever use an estimator if there's another estimator out there that can beat it everywhere? Good question, right? You think we ever teach you about these? Think you ever use them? We teach whole classes on them. So ANOVA is a great example. So if I have 4 different means, group means that I'm estimating, and we'll just consider it balanced one-way ANOVA. So all the group sizes are the same, all of that stuff. If I have these different groups, let's call the different groups their means thetas. So I come up with theta 1 bar, theta 2 bar, theta 3 bar, theta 4 bar, that's the MLE. It turns out, bless you, the MLE is inadmissible. So I'm not going to prove that right here. If you want to see a proof of that, come to my Bayes class and I'll construct an estimator that dominates that. I'll give you a little bit of good news that estimators that do dominate that, they might asymptote right into it. So the MLE has a flat constant function in the typical ANOVA setup. Everything is normally distributed. We can imagine it that way. Measuring group means, the MLEs are just the X bars for those different groups. The risk function is flat. That's all very nice, and it turns out I can find estimators that end up being lower somewhere. The good news is that they asymptote into this line. So this inadmissible estimator that they teach full classes on, it's usually not that bad. So we do use inadmissible estimators pretty often. There's something called Stein's paradox that explains what I'm talking about. So if you want to read about something, look up Stein's paradox. It's not a paradox, it's just a misunderstanding. So again, it's just math stuff. If you want to see how to do that, take my Bayes class. I'll show you the last week of that class. I'll use an empirical Bayes example to try to exemplify that. So we'll do a 2-for-1 in that lesson. That shouldn't bother you tremendously. So it should be a curiosity where you might want to know more about that. Okay, the book doesn't talk about that. I will say that the group means if the dimensionality is 3 or less, it can't be dominated in the ANOVA example, but between 3 and 4 dimensions is the break point where things can be dominated. So very interesting. I didn't understand that. I did not believe it until I was in my final year of graduate school. So I just thought, it's got to be wrong. So I always kind of believed that in the back of my mind until I actually sat down and studied it and understood what was going on. So, and that's why they call it a paradox. So it took people 10 years to go, yeah, the math is right. You know, these are real examples. If they had computers, they could have settled this debate like instantaneously and then thought more about the reasons. Okay, so here's my last definition. An estimator that's not inadmissible is admissible. So I've taken probably the worst route to explain that. I've told you what it's not, but at least you get both sides. So, estimator that is not inadmissible is admissible. So I could just say there's no other estimator that dominates it. So it cannot be dominated. So I have to think about the whole collection of other estimators to think about that. But to think about something that's inadmissible, I just have to think about one other estimator. So that's why I like this route. So I can't draw on board all other estimators. I have to do things like this and make you just think that there's this collection of other estimators. Okay, let me tell you some guarantees about these different estimators. So, theorem. So, unique Minimax estimators are admissible. Do you believe me? Is it obvious? Maybe not. It's kind of obvious once you've done this once or twice. But I remember going, yeah, I don't know. Maybe. I guess I have to think about that really hard. So this picture will help you do the thinking. So that's why I like this picture right here, is I construct my proof right out of a picture, just like this. So what I usually do when I'm trying to prove something is I draw a picture, just to see what's going on the ordering of everything. So I get the concepts, stringing the concepts together into a proof usually takes my imagination a little bit, and I'm usually thinking about a picture. I don't know what the big deal is. If we're not allowed to use pictures to derive things, I get the limitation of that sometimes, and I know how it can lead you astray, but I do think it's the right way to go as a first cursory step. So if I just think about this right here, I can think about what makes this admissible. I know that this point is less than that point because it's minimax, so it's beating its maximum right there. So I know that this function right here for this estimator is bounded by this. So it's got to be bounded by that. Everything has to be lower, that's the definition of minimaximality. I also know that that point has to be higher, its maximum. So somewhere along every other curve, there's a maximum point that's higher. And I can look at that point right there, and I can see that it's that point right here where this is guaranteed to beat that. So the way I set up the picture, this only beats it at one place. So that's why I drew the picture this way, so that you can focus on why this is minimax. So again, this point is less than that, so I can bound everything by that line right here, and I know that there's some point on the other risk function that's higher than that point. So it's at that point that the other estimator, E tilde, takes on its maximum, you're guaranteed to beat it there. You could beat it other places. My picture doesn't do that. So which estimator would I like better in this picture? This is another reason I like this picture, is because I think this is a really good estimator, E tilde, if I didn't believe this was the point right here. If I had low weight on that point, I would think this is a really great estimator. So I like to just throw this out to exemplify the point that minimax estimators aren't necessarily awesome. So they're awesome at a point compared to other estimators, and they're only guaranteed to be awesome compared to one point on that space. But it's making it admissible because you just have to beat the risk function at one point. So my proof is this picture. Let's do this one more time. This thing, so I could say this takes on its maximum at some point. I could call that E theta, or R theta right here. I could bound everything by theta tilde. I could bound everything by the risk it takes on it, R theta tilde. I know that this estimator rises above it at some point because the other estimator is minimax, so its maximum has to be lower than that value. The uniqueness comes in just because I could have some other estimator that takes on this right here, minimax thing, so I could have a third estimator that's coming up right here. It takes on that same maximum, and there's another point that maybe is a little bit lower over here. But it could be lower than that, and so that's why you need unique minimaximality, that they don't have the same maximum risk value. So, because you have something that ties it everywhere, ties it on that maximum value, there's one point that's lower, that's not being dominated by this other estimator. So that's why you need uniqueness. So we could write all that down very colorfully as a proof, but the proof is in the picture. So if you'd like me to go through the details of the proof and writing it down formally, I'd say review session on Thursday would be the time to do it. So see illustrated. I will say, if I do ask you this in any upcoming exam or anything like that, if you just draw a picture like this and say, see picture, I need you to fill in all the little blanks of what I said was lower than what and where it's guaranteed to be lower. So you can't just draw some picture and say, see picture. You need to fill it in with some words. explain what I just said. So you can't point to the picture and say all that, so you need to say it on paper.
Do they discuss Minimax estimators anywhere in the book?
I didn't see it. So I just wanted to fill this in and tell you a few more things that they're skirting over. So they don't give you all these guarantees, but any decision theory book will do it. So yeah, this isn't in the book. There's a little bit going on in the book, and I'll tell you about that. There's another theorem that accompanies an example, and I love asking this example. Oftentimes on finals, I'm not committed yet, I have to wait till your final. We will do a yes, no, maybe before the final, so you can ask me if it's on. Let's get to that example in just a minute. I want to tell you one other theorem. This one's pretty easy to conceptualize. Again, a proof needs some notation. You have to go back to the actual definition of everything and probably use that in the proof, but I'll give you the idea of the proof, which isn't that hard to grasp. So, Bayes estimators using a proper prior. So a proper prior just has the property that pi theta d theta is equal to 1. It integrates. Sometimes people will just give you the kernel of the distribution and they won't normalize this for you, and they'll say something like this, less than infinity. So same concept exactly, they're saying the same thing, they just want to work with functions that maybe haven't been normalized yet, because that's not important, it doesn't change anything. So I'll just say this is a proper prior, it's been normalized, so it integrates to 1. So that might rule out things like using the flat prior across the whole real number line. That's not a proper prior. So that's not a probability distribution. I will say X bar in that example, if we did derive something, if I were doing mu in a normal distribution, I came up with a Bayes estimator, it turns out it does have this property, but it's not because of this theorem. It's because of something else. So, but sometimes this theorem can be used for proper priors. So if you don't like thinking about improper priors, you can just use massively diffuse priors. So I could use like a normal distribution, centered it wherever you want to pick, and the variance is 1 bazillion to the bazillion to the bazillion to the bazillion. So that's proper prior. So you won't be able to compute that on a computer, but at least you get the idea. So this shouldn't bother you too much. Bayes estimators using a proper prior are admissible. And it's not because of where the prior is centered. People say, oh, it's because you centered the prior and you cut information in there and you brought everything down there. And that's not the reason. I've heard that given to me by real smart people where it's like, oh, think about that again. So that's not true. So can anybody tell me a proof idea for why Bayes estimators using a proper prior are admissible?
Maybe they minimize expected risk if theta follows the prior.
What does that mean, if theta follows the prior? If theta came from the prior, if that was the true prior. So it doesn't need to. Yeah, I get that. So theta doesn't need to have come from the prior. So what we're imagining, if we set up a simulation study, how do we pick our thetas? We pick them from our prior distribution. So it turns out it doesn't even need to follow the prior. So theta could have been generated however. Could have just come out of thin air. I just always pick this theta. You pick your prior for some objective reason. So I'll tell you more about that in a Bayes class. So you have good reasons to pick it. I pick it, I like that prior. It happens to be proper, so maybe like a beta half-half or something like that. I have good reasons to do it, but when I set up my simulation and I picked my keys to do my simulation, I didn't sample them from a beta half-half. So like in our simulation example, we ended up sampling our keys uniformly.
Is it because if you minimize the expected loss on something that beats it even at just one point, that expected loss would be lower?
It is true. I don't know if that's a reason. So that's almost like an A is equal to A, so A is equal to
They're
A.
just stating.
It's true, but I don't know if that's a reason.
I don't know exactly, but is it related to the posterior? Like you could rewrite the risk function with the posterior in there.
It's true. Let's just think about it as the original concept. I think that might be a little bit easier, but it's the integrated risk. So I don't know if I even need to think about that. Let me just tell you real quickly. So if something is lower on average, and everything was positive that I was adding up. So that's important. So all this stuff that we're adding up is positive. All the loss functions are positive. So if something is on average lower, it better be lower somewhere. Right? So if I average together a collection of numbers, and it's lower than some other collection of numbers, and they're all positive numbers that I'm averaging together, then in that collection of numbers that's the average is lower, there had to be a lower number in there. So you could turn that into a proof. If it's average on average lower, then it needs to be lower somewhere. That's it. So we could adorn that with a proof. A proof might look like, let's assume that it didn't happen. So let's say it's a Bayes estimator, and that it's not dominated. So there's some other estimator out there that dominates it. So it's not admissible, so it's been dominated somewhere. I could show that that estimator has a higher average, and I'd come up with a contradiction. So if you want to go through a formal proof that looks like that, we can do that. But if I average a bunch of positive numbers together and they're lower, then it has to be lower somewhere in that set. So almost a proof. So we could go through the details of that. I usually do the contradiction proof because it's 1 or 2 lines. If I need more than 1 or 2 lines to prove something, I won't use a contradiction proof. So just out of style. And anybody that's a math major can tell you the reason why. So what's the reason why? Okay, there's other types of proofs. But why is a contradiction proof not necessarily great if the proof is really, really long? You could have an error in your math. So you could have had an error, and that's what you're contradicting, is I just got an error in all of this. And so you end up going, oh, contradiction, when you made a mistake. So I think that's the reason. So I'll use contradiction proofs if it's like 1 or 2 lines. Let me tell you one more thing. This is true regardless of the propriety of the prior. I will just say in terms of the averaging with proper priors, improper priors, weird things can happen if I have weights going off to infinity. So infinity does weird things. So if you don't weight using things that explode, so then this is a true. It could be true even if I don't use a proper prior. So X bar in the normal example would be an example of when I get back that same estimator. If I use a flat prior, I will get X bar back. Saying that that's not the, I can't apply that theorem to say that it's admissible. X bar is admissible. X bar is minimax in that example. So I could use the minimaxmality and say, oh, it so happens to be minimax, and just use that proof. Okay, one more. There's a problem in the book that addresses this. I'd like you to look at it. So, Bayes estimators with constant risk are minimax. So that means that the risk function that you end up getting is flat. So when I take R e pi theta, so I'm not taking the Bayes risk, I'm just taking the risk function. So no matter how I've gotten an estimator, I can always plug it back into a risk function and draw its curve. So if it's constant, it's guaranteed to be minimax. Some people will call this the least desirable minimax estimator, because you could have other estimators out there there may be Minimax that do something like this. So, and come down a little bit. How would you set up a proof like this? So you would end up saying, if this weren't true, right there, I could build up some other estimator that's Minimax and somehow it has higher risk, but it can't be true if it's flat because that's going to maximize this area. And we're minimizing that area, so we're finding the minimal rectangle sort of area under this curve. So again, you could do a contradiction proof to prove that. So a constant risk Bayes estimator, because it's lowering everything on average, has to go through the Minimax point on the risk curve. So you cannot have an estimator that does this right here because it's going to minimize the area, and this one should be minimal. So this is kind of the proof construct that you would use, or at least the picture, to prove this. But that's kind of a cool thing. So it tells me that a lot of this is just really cheap definitions. Minimaximality happens because of what happens at a point on other estimators' curves. So I'm just beating it at one point at least. Hopefully you do a little bit better than that. So minimaximality is kind of a weak concept in its own. And I would say admissibility of Bayes estimators is a pretty cheap concept on its own, just because I can do it with any prior that's proper. And I can say, well, it's admissible, it beats something somewhere. So just because it beats something somewhere doesn't make it necessarily great. Sometimes I feel like I'm inadmissible when I meet certain people, that it's like they do all these great things, it's just amazing, they're great musicians, they're great athletes, they're great academics. I hate that. So where it's like, well, they do everything I do, yet better. And then I hang out with them for a little bit longer and I find out there's something I do that makes me admissible. And I think that's true for all of us. So we'll just leave on that positive note. We're all admissible. We just have to search over theta and do the comparison in the right way. You'll find the areas where you're better than somebody. Anyway, if you want to prove these, we can do it on Thursday and go through formal proof constructs, or you can kind of do it yourself. So I do accept pictures so long as you're telling me what part of the picture to look at. So as long as the concept is conveyed, I accept those as proofs. So I even do that on the qualifying exams. I just don't think it's that big a deal. And I get a permission slip because I was a math major. So I did all that work and I sometimes go, yeah, but I still just go. So I think that's okay. Dylan, do you disagree?
As the sake of the other professors agree with you.
It doesn't matter to me. But for you, it might. So I'm just letting you know what matters for me.
And diagram proofs, I have that problem. Certainly.
Yeah, so you got to see different people with different things sometimes.
It's so clearly that diagram shows that set relation.
One truth is that you can't please everybody with the same argument. That's always true. That's the only thing you can guarantee. Or that you never will know things for certain. You can guarantee that. That's it, you guys. We'll come back on Friday and start up on hypothesis testing. So what I'm going to tell you in hypothesis testing is there's trade-offs. In any decision you make, there's two different types of errors. And you have to think about the trade-offs between those different errors. Well, same thing happens here with decision theory. There's trade-offs in everything. I've shown you an estimator in a picture that is optimal at a theta star at some, or mu star at some point. But if I use an estimator like that, if the truth wasn't mu star, then I might do exceedingly bad. So just like anything in life, there's trade-offs to everything. So we have to come up with good mechanism to try to balance those trade-offs. And there's many ways to do it. And that's one of the things that people are arguing about in hypothesis testing, is what the trade-offs are. So, but they're arguing over some version of trade-offs. And I would say, if you don't understand the proofs in the math, it's really hard to have that argument. So we're going to go through that and try to figure out what these different proofs are talking about. If you want to see the hard part that we're going to do in the next week and a half-ish, just over, name it Pearson. So start studying that proof. That's it. Thank you guys.